Thank you for attending this talk. My topic is about cosmological standard timers in primordial black hole scenario, based on these two papers. My name is Qianhang Ding from the Hong Kong University of Science and Technology. This work was done with Yifu Cai from USTC, Chao Chen and Yi Wang from HKUST. First, let's take a look at the history and evolution of our universe. If we would like to know how does our universe evolve, we need to know how to measure the universe. At present, we have many methods in measuring the universe, such as the standard candle and the standard ruler. In standard candle, we have the absolute luminosity of type 1a supernova. By measuring the apparent luminosity of them, we can obtain the luminosity distance, which help us to measure the universe. In standard ruler, we have the sound horizon from the baryon acoustic oscillations. By measuring the angular separation, we can obtain the angular diameter, which can also help us to measure the universe. However, with this measurement, we still have potential tensions in cosmology, such as the Hubble tension, the Hubble parameter measurement at the early universe. It's not consistent with Hubble parameter measurement at the later universe. We don't know whether is there some systematic uncertainty in these measurements, or is there some new physics in cosmology, which may push us to find a new way to measure the universe. First, let's take a look at these 100-meter games in Beijing Olympic. Maybe it can inspire us to find another way to measure the universe. If we imagine this 100 meters as the history of our universe, the start point is the Big Bang, the finish line is the present universe. The condition of the player can be described by this timer, and the condition of the universe can be described by the evolution of the scale factor. Therefore, maybe we can use a cosmological standard timer to describe the evolution of the scale factor, which help us to understand the evolution of the universe. So, how to know the elapsed time in a timer? First, we need to know its initial state, then final state, and we integrate its internal dynamics. For initial state to the final state, we can obtain its elapsed time. Next question is how to obtain the evolution of scale factor. In this equation, we all know that if we can know the evolution of redshift, we all know the evolution of the scale factor. In our universe, we have a lot of dynamical systems. And by studying their dynamics, we can know their physical evolution time. And these dynamical systems also emit the cosmological signals, such as the electromagnetic wave and the gravitational waves. From these signals, we can extract the cosmological redshift. Then we can relate the redshift and the physical evolution time, which tell us the evolution of redshift and further give us the evolution of scale factor. So, how to construct a standard timer in dynamical systems? For a dynamical system, we have a standard initial state, which is their initial statistical distribution. And for their final state, which can be described as the statistical distribution at the physical time Tn. And we study their dynamics, and from the initial statistical distribution to the final statistical distribution, we can obtain the physical evolution time. However, in our observation, usually the cosmological redshift appears in the observable statistical distribution. We can then the redshift can be extracted from the observed statistical distribution. as a result, the redshift and physical evolution time is related, and we can know the evolution of redshifted, which further give us the evolution of scale factor. So the fourth dynamical system we consider is the primordial black hole clustering, which was studied in this paper. And the initial state we choose in PBH clustering is the primordial mass function of PBHs, which is the log-normal mass function in inflationary scenario. So first question is how to extract the physical evolution time in PBH clustering. We need to study the evolution of PBH mass function. The PBH mass function at the physical time t can be described as the initial mass function times the PBH mass involved from the initial mass to the later mass. And from the mass evaporation relation, we can find that PBH mass function at physical time t can be described by the initial mass function times distance. In order to know the physical evolution time delta t, we consider a small mass limit. This small mass limit, the PBH mass function at physical time t is proportional to the m squared, and the factor depends on the initial PBH mass function and the physical evolution time. Therefore, we can obtain the physical evolution time in PBH clustering. So, can we see PBH clustering? In this paper, we show that if the characteristics mass of PBH in PBH clustering is around 10 to 15 grams, and the total mass of PBH clustering is around 1/3 mass, we can observe PBH clustering. And with a suitable total mass of PBH clustering, we can observe them up to the redshift 1000. The next question is how to extract the redshift from the observable. The observable form of the PBH clustering is a Hawking radiation. So the Hawking radiation emitted from the PBH clustering can be calculated by integral the PBH mass function with the Hawking radiation kernel. We can obtain the Hawking radiation spectrum. After Hawking radiation propagate from the PBH clustering to the Earth, the observed photon flux is observed and can be expressed by this expression. Because we need to relate the physical evolution time and the redshifted. However, here redshift appears with the photon energy, not with PBH mass. So we need to transfer this redshifted from the photon energy to the PBH mass, and from the properties of Hawking radiation kernel, we can find that the observed photon flux can be expressed by this integral equation, where the redshifted mass function appears. However, here, in order to obtain the PBH redshifted mass function, we need to study a inverse problem. For an integral equation like this, in order to obtain this Fn, we can apply a inverse kernel on this PE function, which gave us the Fn. So here, in order to obtain this inverse redshifted mass function, we need to apply a inverse Hawking radiation kernel, which gave us a redshifted mass function. After obtaining the redshifted mass function, we compare it with the initial mass function, we can obtain the redshifted. Then the relation between the redshift and the physical evolution time in PBH clustering is obtained, and we can construct the physical evolution of redshift, and then give us the evolution of scale factor. The next dynamic system we consider is the primordial black hole binaries, which was studied in this paper. The initial state we consider is the initial probability distribution on major axis A and the eccentricity E. So first question is how to extract the physical evolution time in PBH binaries. Then we need to study the evolution of probability distribution in PBH binaries. Its probability distribution at the physical time t can be described by its initial probability distribution times a Jacobian. And this Jacobian can be calculated from the orbital parameter involved from the initial physical time to the late time. And from the evolution of its orbital parameter, major axis and eccentricity, we can numerically calculate this Jacobian, which gave us the physical evolution time. That's t. So then, can we see the PBH binaries? In this paper, we show that with the different PBH density in our universe, the LISA can observe PBH binaries up to the redshift 1000. Next question is how to extract the redshift from the observable. The observable of PBH binary is the gravitational wave from them. By studying their gravitational wave, we can extract the redshifted chip mass of PBH binaries. In order to obtain the redshifted, here we need to know, we need to collect a number of PBH binaries from the same redshifted, and by compare its probability distribution with the initial probability distribution, then we can obtain the redshift. However, from the redshifted chip mass, we don't know the redshifted. We don't know its chip mass. Or the only things we know is the redshifted chip mass. But here we can assume all the PBH mass are same. Therefore, if we can obtain a number of PBH binaries with the same redshift chip mass, that means this is PBH binaries must come from the same redshift. Just like this figure, for PBH binaries from the different redshift will give a different redshifted chip mass, and under the assumption that all the PBH mass are same. After obtaining a number of PBH binaries from the same redshifted, we can obtain their probability distribution, redshifted probability distribution, by compare the redshifted probability distribution with the initial probability distribution. We can numerically solve the cosmological redshift. And after obtaining the redshift and the physical evolution time, we can construct a standard timer in PBH binary systems by studying their evolution. So here we have already obtained the redshift and the physical evolution time relation in two dynamic systems, PBH clustering and the PBH binaries. And we can apply the relation between the redshift and the physical evolution time into this equation, which can give us the constraint on cosmological parameter, such as the Hubble parameter H0, the density, omega gamma, omega m, and the omega lambda, which help us to understand how does our universe evolve. Thank you.